Alrighty, so last class we went over some basics of solutions. We defined what a solution is, what a solute and the solvent, unsaturated, saturated, supersaturated solutions, how does a dissolving happens, and that solute and that solvent needs to swell up before it can start mixing. And as it's doing that, it's going to look at the things that are trying to dissolve and determine, okay, are they polar or not? If they're polar and the solution is polar, it will dissolve. If it is not polar, non-polar, and the solution is polar, then it will not dissolve because it will create an immiscible solution. So like dissolves like, so polar dissolves polar, non-polar dissolves non-polar. So don't forget that. We did some examples on that. We briefly went over electrolytes that have to do with ions on solutions. The more ions, the stronger the electrolyte is, the more it conducts electricity. We talked about solubility curves a little bit. Under the curve, unsaturated. On the curve, saturated. Above the curve, supersaturated. And we also spoke about solubility of gases, which do the opposite of solubility in liquids, of solids in liquids. Because gases, solubility decreases with temperature because more gas gets out of the liquid, so it doesn't stay in the liquid phase. Okay, then we jumped into the equations from Chem 1 that you should know and remember: mass percent, mole fraction, molarity, and molality. We have molality because not all problems can be solved with molarity. Molarity is a temperature dependent calculation because it deals with a solution. Molality does not depend on temperature. And some of the equations we'll see today deal with molality because we're doing things with temperature. So we don't want temperature to affect the results. I believe we did a problem on how to convert from molarity to molality, which is problem number 1 in your handout. We did this already. I put all the steps, and this is available on Annotate, so you can download it and look at it more carefully if you want. We compare the factors between solids and gases in terms of solubility because of temperature and pressure affecting them. And that takes us to what we have to start with today. So we have Henry's law and gas solubility. So solubility of a gas is affected by the amount of solution in there. That's another law that we had to look at the end. But Henry's law says that the solubility depends on the partial pressure of the gas above the liquid times a constant that we call the Henry law constant. The bigger the constant, the higher the solubility of that gas. So when we talk about solubility of gases, because being soluble in a liquid, we use just this law. This is a quick calculation. So for example, the Henry law constant for hydrogen sulfide in water at 25 degrees Celsius is 0.087. Determine the solubility if the pressure goes to 3.50 atmospheres. So we have the partial pressure of 3.50. We know the solubility constant. So multiply the solubility constant times the partial pressure, and we end up with a solubility of 0.30 moles per liter. We have a problem in your handout that we're going to do later. I have it set up for later. Okay, just reinforces the thing that we can use those solubility constants to compare which one will be more soluble or not. The rule is the higher the solubility constant, the higher the solubility of that gas in a liquid. So if I have a value of K that's higher than 0.087, by definition, it will be more soluble. If I have a value of K that's lower than 0.087, it will be less soluble. And for Henry's law, that's all I am going to ask you. I'm not going to ask you to do anything else. Just plug in the numbers in the equation and calculate what the solubility will be and maybe compare between two things and which one will be more soluble or not. That's all I'm going to ask you to do. I'd rather spend my time doing other type of problems. Okay, this we know already. Intermolecular forces are between molecules. Intramoleculars are within the atoms in that molecule. And that has a big effect because intermolecular forces determine a lot of properties on matter. And we went through all those on chapter 10, so I'm not going over those again. Now, we did this already. Now we have a new situation. Okay, today we're going to be able to play, okay, why is it that we throw salt on the road when it snows? Why all those people in New York and up north with all those snowstorms throw salt on the road? You're adding salt to the snow. What is that doing? We'll be able to explain that today. So, but before we can do that, we're going to define this thing called colligative properties. And these are properties that only depends on the concentration, not on the identity. I don't care what the solute is. All I care is the concentration, how much I have of that solute in it. The more solute, the more the properties are going to be affected. The less solute, the less they're going to be affected. And let's not forget that we have molarity, molality, and mole fraction that we're going to have to use somehow in a specific way, because they are going to affect either the vapor pressure, the boiling point, the freezing point, or this thing that we call osmotic pressure. So there's different things that can be affected by the amount of solute. Remember, we don't care about the nature, the identity. We care about how many you have. So when we look at it and we have the liquid phase, we can go in either of two directions. We can either go towards the solid, so that liquid turns into a solid, or we can go towards the gas, so that liquid turns into a gas. And for that liquid to change to a gas or a liquid, it has to go through the freezing point or the boiling point. And we can play with those melting points and boiling points, and we can change them by increasing the boiling point or decreasing the melting point. So we want to decrease the melting point so water stays as a liquid longer before it turns into ice. Or we can add a solute to the liquid phase so it takes longer to evaporate. So if we look at our triple phase diagram, you remember we have the three phases: solid, liquid, vapor. Basically what we're doing is expanding this liquid phase by changing the boundaries of where they occur. And when we move the liquid boundary towards the right, we are elevating the boiling point of that substance. And we move the boundary of the liquid towards the left, we are decreasing or depressing that freezing point. The triple point stays the same in there. And we're going to have a delta TF for freezing and delta TB for boiling that we need to be able to know how to calculate. And we have two equations. They are the same equation. The only thing that changes is the type of constant it is. For boiling is Kb, for freezing is Kf, and then you have the molality in there. Again, we're using molality and not molarity because molality does not depend on temperature. We don't want that molality affecting how the delta T changes because it's going to be determined by these constant values that we have in here. Don't forget, molality is calculated as moles of solute or kilograms of solvent. So we have two equations. We're not done with equations. There's a little more we have to do to that equation because I mentioned we don't care about the nature of the substance. We care about the quantity or the amount. So we do have to account for that. And the equations, the way they are written right now, doesn't do that. So we are going to define this Van Hoff factor, I. And the Van Hoff factor is how many ion types you have in solution. For example, if you have sucrose in water, it just takes as molecules of sucrose. So the Van Hoff factor is going to be only 1. And we are going to summarize it by saying all molecular compounds have a Van Hoff factor of 1. So it could be sugar, it could be sucrose, it could be anything molecular. The I value is always 1. When we start ionic compounds, for example, NaCl, because NaCl breaks into sodium and chlorine, 2 different type of ions, the I factor will be 2. 2 ions types, Van Hoff factor of 2. If I have 3 ions, the Van Hoff factor will be 3, and so on. If I have 4 ions, I will be 4. We're just going to do it like that. So you're going to look at the ionic compound and determine into how many ions it divides into. To determine the I factor, and we are going to plug it into the equations I just gave you by just multiplying by that factor. So the more ions you have, the more that freezing point is going to change, the more that boiling point is going to change, and the osmotic pressure will change as well. We haven't done anything with osmotic pressure yet, it's coming. But I just wanted to throw all 3 together because they're all affected the same way. So if you do calculations without considering the I factor, you are not taking into consideration the amount of that solute. That will be a big mistake because it's a big, big factor in it. So if you throw regular salt into ice, it will melt and that freezing point will change. But if you change the type of salt you use, and instead of using NaCl, you use something like calcium carbonate. Calcium carbonate will have, that one is 2 too, but you can find a different one that has more than just 2 ions. It will increase the I factor, that freezing point will change more. What means is that the liquid will remain a liquid for longer before changing into a solid, because that delta T makes it change more. The lab you are doing today, you are going to use the freezing point of a solution. You're going to calculate that the freezing point of a pure solution by measuring the temperature changes into a solid, and you'll be able to see that change and measure that using the vernier probe. And then you're going to add an impurity to it, which means adding something to it, and see what the delta F will be. And then using that delta F, you are going to calculate the molar mass of the substance you are using. And you'll have all the information you need because you'll be able to calculate the delta F. You'll be able to calculate that I. You will have the K factor. And then from the molality, you'll be able to calculate the moles, and knowing the mass that you're using, you'll be able to calculate the molar mass. Yes.
What is the I factor exactly? Like, what is it exactly? The I factor.
The I factor is how many ions of solute you're using. It takes into consideration the amount of solute you have.
The ions of solute?
Well, it takes into consideration the amount of ions of solute you have in solution.
Okay.
So remember, when you add a ionic compound into a liquid, it dissociates into these ions. So the more ions you have, the bigger that I factor. And the more effect it has in the properties. Okay, so I'm going through all the theory, and then we'll look at the problems. Now we have this osmotic pressure. Have you guys heard about it before? No? It's okay if you say no. Have you guys heard about reverse osmosis? You know what it is? Well, you will today. But that's part of this. Osmotic pressure is used a lot in biology. A lot at cell levels. So we'll be able, well, we're gonna get into it in a second, of what this osmotic pressure means, because we have to take into consideration the type of solution and solvent we're using, and we are going to calculate that osmotic pressure based on the molarity RT, because in this case it's temperature dependent. And like I showed you in a slide before, or 2 slides before, we still have to add that I factor in there as well. So let's look at it more carefully. Normally, you guys have heard about diffusion, right? And diffusion is what? The movement from what to what? High concentration to low concentration, high concentration of solute to low concentration of solute. So it moves towards the low concentration, so until we get an equilibrium of particles on both sides. So right now, we have a pure solvent on the left, we have a semi-permeable membrane in the middle, and then we have a solution on the right. If we look at the particles are going to try to move from one side to one side. Left to right or right to left? Based on the definition I just gave you. Where do we have more particles, on the left or the right? On the right, so the particles are going to try to move towards the left. That is if we look at the solid. If we look at the liquid, where do I have more liquid particles? Left or right? Left. So the particles are going to try to move towards the right. As those particles of water start moving to the right, the height of the right side is going to start increasing. By that side start increasing on height, that's going to add a pressure to it. That pressure is going to keep increasing until no more flow of water particles happens between the two sides. When that happens, they are at equilibrium. There's no more net flow of particles of water, and we call that osmotic pressure. So osmotic pressure is the pressure in equilibrium to stop the flow of water particles. Now, I can force those particles to move from right to left by pushing down on that column. That will make those water particles move towards the left. This side will get more concentrated on solute, and this one will get more pure water. So reverse osmosis is what they use to purify water by reversing the natural flow of water towards the side where there's more water. And by doing that, it removes all the impurities from water, all the solids that might be in it, and you get drinkable water. So that's what when they go door to door knocking on your house, do you want a system to purify your water? That's most likely using reverse osmosis, because it's pushing the flow of water in the opposite direction it wants to go. Doing that makes the left side have more pure water than the right side. So because all the particles are going to stay on the right, that semi-permeable membrane is not going to allow those particles to go to the other side, because that membrane is there to only allow the flow of water. Solids do not flow through that membrane. Okay. Now, if we look at this at the cell level, and this is just a little bit of biology, we have our cells in our body. Depending on how much you have outside the cell or inside the cell, three things could happen. The things entering the cell or leaving the cell is the same, so it's at equilibrium. We call that isotonic, because water is going in, water is going out at the same rate, nothing happens. If more water starts going into the cell than is going out, then the cell is going to start swelling up until it bursts. We call that a hypotonic case, which is, in medical terms, hemolysis. Or we can have the case where the water is leaving the cell too much because the environment around it has less water, and that we call that crenation, because the cell denatures, it changes because it's losing all the water it has inside. The hypotonic and hypertonic cases are not desirable because they come with their own problems. We want an isotonic case because it's at equilibrium. That's why when you eat a lot of popcorn, they know if you put a lot of salt in the popcorn, you have to drink a lot of soda. That's how you get your money. Because you buy popcorn, you have to buy soda because you're going to be too salty. The movie theaters know that. That's why they jack the price of the soda and they sell you the popcorn for less. Because your tongue is going to start losing water, so it's becoming hypertonic. And we need to move towards the left, towards the equilibrium side. So the only way you can do that is by drinking water. That's why when you have a lot of salt, a lot of salts in your blood, they have to put fluids on you, need an IV, because they need to pump more water into your blood so the cells can receive the nutrients and all the liquids they need. Now, that's a lot of biology. We are not going to spend more than just mentioning this. The last thing we're going to do for this chapter before we look at the problems is that when you start having particles in solution, and those particles are solid, we are going to form this thing that's called a colloid. And a colloid is just suspended solids in a liquid. Depending on the size, we call it colloids or whereas suspension, and the only difference is that colloids, the particles have to be between 1 and 1,000 nanometers. Suspension, because the particles are greater than 1,000 nanometers. That is how soaps work. When you go and take a shower, and you're oiling, and you use soap to clean yourself, the soap is reacting with the oil and trapping the oil particles. It's not just soaping myself and I get clean. There's a lot of chemistry behind it because you have to look at the polarity. Oils are invisible in water, so soap needs to be able to do something to the oils to be able to remove them. And they do that through emulsification. Emulsification is something that they add to the soap, so it has a hydrophilic and hydrophobic side to it. So it attracts the water, but it also attracts the oils. So it attracts the oil by trapping them, but it attracts the water, so it goes in your body and clean and trap those in there. So there's a lot of examples that we can do with colloids. The only other thing I will mention is that depending on the size of the particles, we have this thing called Tyndall effect that affects how light scatters through the liquid. So if I have a solution and I throw light at it, depending on how big those particles are, is how that light is going to diffuse through that liquid. And they use that for light shows and other things because they can control the size of the particles and how that light is going to expand. Okay, so this is more of a definition thing. We're not going to do any type of calculation with it. Just to summarize and close the chapter, for gases, you have Henry's law. You can calculate the solubility based on the partial pressure of the gas, times the solubility constant for that gas. When we deal with the solubilities, don't forget the rule: light dissolves light, polar likes polar, non-polar likes non-polar. We have molality versus molarity. Make sure you know when to use each. We also have boiling, freezing point calculations. The delta T is important. It has a lot of applications. Then we have osmosis that we saw. And the last thing that we haven't done is vapor pressure calculations under Raoult's law, which we'll do after we do some examples. Don't forget, temperature has to be in Kelvin for gases and osmosis calculations. And that pressure usually has to be in atmospheres because that R constant is probably most likely in atmospheres as well. Okay, so that takes care of this part.